Okay, hello everyone. Welcome to today's lecture. My name is Alicia and I'm going to be taking you guys through our QCE Specialist 3 and 4 July lecture. So, let's get started. Here is the content in Units 3 and 4 that you have been going through. Probably at this point you have almost finished this content. So in Unit 3, you've done proof by induction, vectors and matrices, and complex numbers. And then in Unit 4, you've done integration and applications, rates of change and differential equations, and statistical interference. The content that we're going to be going through today are these two last green dot points here: rates of change in differential equations and statistical interference. So, here is a quick overview of what we're going to be doing today. We're going to start off with our topic 2, Unit 4, modeling motion. And then we're going to move on to topic 3, Unit 4, which is statistical interference. And we're going to have a look at sample means and confidence intervals. After that, we're just going to spend a little bit on my external exam advice. So things that I learned from when I was in year 12. Just a few quick announcements as well. These slides are available for download, so make sure you download those for just to help you write down your notes, anything to add to your notes, and then also for revision purposes when you're getting closer to your external. This is a recorded lecture and it will run for 2 hours. So the benefit of that is that you can pause if you need to write anything down, or you can come back and finish it later or watch it at a different time to when it is initially live streamed. However, there is a live chat, so please feel free to ask any questions at all and I'll be available to answer them. So you can ask any questions about, say, any content that we're going through, an example that you didn't quite understand, any of the content, even if we didn't cover it today, anything in different subjects that I did as well. If you have any questions about content from different subjects, anything about juggling all your subjects, study skills, your ATAR, uni, anything like that, I'd also be very happy to answer. So, before we get on to the content, a little bit about me. So, I graduated in 2021. I'm currently studying law and economics at UQ. I got an ATAR of 99.55, and I got an overall score of 96 in specialist. So the breakdown of that was I got a 20 in the assignment, I got a 15 in one of the internal exams and a 14 in the other internal exam. And then in my external, I got 47 out of 50. So I lost more of the marks in the external, but I mean, that is definitely to be expected. Alrighty, so quickly before we get onto the content, this lecture is provided by ATAR Notes. So ATAR Notes provides a lot of free resources, including study notes, lectures, community videos, newsletters, forums, articles, and the infamous ATAR calculator. And we also provide a tutoring service called TuteSmart from previous QCE graduates, study guides, and Ed Unlimited as well. So, now we are getting onto the content. So, let's start with what the modeling motion section of the syllabus actually requires you to do. So, the syllabus requires that you are able to examine momentum, force, resultant force, action, and reaction, consider constant and non-constant force, understand motion of a body under concurrent forces, consider and solve problems involving motion in a straight line with both constant and non-constant acceleration, including simple harmonic motion, and use all of those expressions below for acceleration. Those are all on your formula sheet as well. We'll get to those. And this is what you need to be able to do for the modeling motion section. Just another quick tip as well is to make sure that you understand the difference between the cognitive verbs, and that's available on the QCEE Specialist syllabus under definitions. So the cognitive verbs are underlined here. So examine, consider, understand, consider, and solve. This isn't as relevant for the math subject, specialist in methods, but it still is useful. It is more so useful for your sciences, where there is a difference between like defining and then explaining and solving. But most of the cognitive verbs in specialist are going to be centered around solving. All right. So, what we're firstly going to focus on is momentum, force, resultant force, action and reaction, and constant and non-constant forces. So, momentum is given by mass times velocity, right? And force is the rate of change of momentum in a system with respect to time, or in other words, dp dt. So we have a relationship already between momentum and force. We also know that force is equal to mass times acceleration, which is also known as one of Newton's laws, where the units for force are newtons, or in other words, kilogram meters per second squared. So, force, acceleration, velocity, and displacement are vector quantities, which means they have direction as well as magnitude. So make sure you always give direction in your answer. This is really important. It's really easy to forget direction, especially if it's not something where you need to find an angle. If it's just kind of like upwards or downwards, make sure you still write that. And then make sure, of course, if you're finding a vector quantity, that if you need to find an angle direction or a bearing or something along those lines, make sure you find that too, because otherwise you'll lose a decent chunk of marks out of the question for that. All right. So this kind of stuff we've just gone through is pretty basic stuff. But I'd say the most important to remember off this slide is F equals ma. Of course, I guess most people know of it, but what I'd recommend doing is in your notes, make sure you kind of highlight it or put it in a different color, because a lot of the time when you're doing one of these modeling motion questions, if you come to a point where you don't really know where to go, one of the options you can usually apply is F equals ma. It's kind of one of those equations that you maybe forget about, but realize that even though it's not on your formula sheet, you can actually apply it. Alright, so these definitions that I've given aren't wrong, but they're not really that practical by themselves, because in reality, there are lots of different forces acting on a particle, not just kind of one force in one direction. A lot of the times we have particular forces all pulling in different directions. We might have an applied force and wind or friction, a lot of things going on at once. So, what we usually deal with in specialist is the net force, and the net force is the sum of all of the forces acting on an object, right? As a result, our resultant force is given by F net equals the sum of F, right? The sum of all of our forces. Again, you don't really need to remember this equation, it's just a concept you need to remember. So, as a result, to find the acceleration of an object as a result of a few different forces acting in different directions, we need to know the net force and the direction of that force, because we know that F net equals ma. So to find the acceleration, we need to have the mass of the object, and then we also need to have the net force, right? So a lot of these questions that we're doing when we're getting into modeling motion look at finding the net force. So usually what we're going to be doing is looking at a few different vectors, adding the components of those vectors together, and finding a resulting force. So typically what we need to focus on is mostly just kind of vector resolution. When we get into more difficult like rates of change and stuff like that, it's more focused on the actual equations in your formula sheet. But when we're getting into this kind of modeling motion and understanding net force and momentum and all that kind of stuff, it's really just about vector resolution. So let's have a look at actions and reactions. So the action is the force of one particle on another, such as pushing a door open. And a reaction is a consequence of Newton's third law. So this is where the second particle exerts an equal and opposite force on the first, i.e. the door exerts an equal and opposite force on your hand. And this is what you feel pushing back against you. So, some common reaction forces you might encounter is tension, which is a force through any string, chain, rope, or kind of any like similar like string-like object. And normal force. So normal force is the force opposing gravity that an object exerts on another. One thing I just want to make note of with regards to tension, if you're ever asked about tension in a question, the force of tension is just equal to the force applied through that object, right? So if a question tells you that there are, 10 newtons of tension applied through a string, that just means that the applied force is 10 newtons. There's nothing special about it just because it's tension, right? The only time you really need to consider the fact that it's a string, chain, rope, or whatever is where you kind of have like pulleys and you have like maybe multiple masses on pulleys. But again, you're not really focusing too much on the fact that it's a string, chain, or rope. You're mostly just focusing on the effect of the masses on one another. Anyway, just a quick little note in case you're getting confused about that. And again, with normal force, remember the normal force always acts perpendicular to a surface. Where you might see this in Specialist is if you're doing an inclined plane question, and you do come across those in externals and mocks. If you have an inclined plane, the normal force is perpendicular to the plane. It's not perpendicular to the ground, right? So what this might look like is an inclined plane like this. The normal force will look like this, right? It's not going to be perpendicular to the ground, it's perpendicular to the plane. Alright, just because the forces acting on both objects are the same doesn't mean the result on each object is the same, and this is Newton's third law. So this is the very classic example, I'm not sure if you've heard of it, of a person and a spaceship. I think it was one of the first um, uh, expeditions out in space, and they took an astronaut out to space, and they tethered him to the spaceship, and he went off and explored around in space in his spacesuit. Then when he went to try and get back into the spaceship, he couldn't, because every single time he touched the spaceship, he just kind of bounced off, like quite violently, right? Um, and everybody was really shocked and confused. They were like, why is this happening? Right? Until eventually they realized, this massive team of physicists and experts taking people up to space realized that they forgot about Newton's laws, which is that there will always be an equal and opposite reaction to every action. So, when the astronaut was touching the spaceship to try and get back in, he was exerting an action, right, which was moving the spaceship a tiny, tiny, tiny bit, because it's very big. So he's putting in action, and it's moving the spaceship a tiny bit. But the spaceship is making him bounce back because he's so much smaller. So it's exerting an equal and opposite reaction on him, but he's experiencing it far more because he's so much smaller, that it requires a lot less force for him to move. And this is exactly the concept that we're seeing here in this question. So, we have a sumo wrestler with a mass of 200 kilograms running into a gymnast with a mass of 40 kilograms. As they collide, the sumo exerts a force of 800 newtons on the gymnast. Find the force exerted by the gymnast on the sumo and the resulting acceleration experienced by both people. Right. Pause the recording, have a go at this question if you're feeling confident. If you're unsure, don't worry about it. We're just going to go through the solution now. So, let's quickly draw a diagram of what we're seeing. So we have our sumo wrestler, right, running into a gymnast, right? So the sumo exerts a force of 800 newtons on the gymnast. Find the force exerted by the gymnast on the sumo, right? So remember, every action has an equal and opposite reaction, meaning that the force exerted by the gymnast is going to be the same. It's going to be 800 newtons. Now we need to find the resulting acceleration experienced by both people. And this is going to be different because both of these people have significantly different weights, which means it requires significantly different amounts of energy to move them. So, what we know is that F equals ma. So the force exerted is 800. The mass of the sumo wrestler is 200, a sumo. This gives us an acceleration of 4 meters per second, and this is just going to be away from the gymnast. Applying this again for our gymnast, we're going to have 800. Her mass is 40, a gymnast, and this gives us an acceleration of 80 divided by 4, which gives us 20 meters per second away from sumo wrestler. We don't actually have the directions, I don't believe. No, just that they're running into one another, so we can't provide whether it's left or right or up or down or whatever. And the force exerted by the gymnast on the sumo will just be, I guess, like towards the sumo. So, as you can see, the acceleration experienced by the sumo wrestler is a lot less than the acceleration experienced by the gymnast, and that's because the gymnast is so much smaller. Alright, now what we're looking at is a more difficult example. So in the previous example, our two forces were acting in the same plane. They were acting directly against each other. In this example, however, they're not acting in the same plane. So, as a quick tip, when there are multiple forces acting on an object, it always helps to draw a diagram of what's going on. Here we have two people pulling on a rock. Both people exert a force of 1,000 newtons, but person A pulls to the right and person B pulls upwards. What is the net force on the rock, assuming a smooth surface? Normally, when we're given two forces acting in different directions, instead of just head to head or tail to tail like we were just before, with the sumo wrestler and the gymnast, what we need to do is resolve forces into horizontal and vertical planes. Or what you can also do is you can draw your forces as vectors if you have the angles, and you can use like trig and angle rules like the Z rule and co-interior angle rules and so forth to actually do some vector resolution, just depending on what works for you. Alright, so for this example here, what we're going to first do is draw a diagram. So, both people exert a force of 1,000 newtons. And person A pulls to the right and person B pulls upwards. So, person A, person B. Both these arrows, 1,000 newtons. And we want to find the resulting force, F net. Have we missed anything? No. So, here we have I and J. Alright. As you can see here, our vectors are added head to tail, which is what we need to do to find our net force. So, as you can see here, we have a right-angled triangle because our horizontal line is directly horizontal and our vertical line is directly vertical. So it's a right-angled triangle, meaning we can just actually use Pythagoras to find our net force. Squared, and we're going to have 2 times 1,000 squared. And this is going to give us 1414.2 newtons. And now we need to find the direction at which this force acts. Because remember, force is a vector quantity, we need the direction and the magnitude. You could use trig to come up with this angle here, but for me personally, because this is an isosceles triangle, we already know that this is going to be 45 degrees to the horizontal, because it's an isosceles triangle. But you can just feel free to use just use trig there if you'd like. Another way you could have recognized that is remembering our special triangle, the isosceles one, how this angle is 45 degrees. So you could have done it that way as well. Alrighty, so that was our question there. Pretty straightforward. Now we're going to move on to an even more difficult one. So here we have a picture hanging up. Suppose that A and B are the forces of tension of the two cables hanging the picture up. These forces are both 50 newtons, and the angle each cable makes with the horizontal is 30 degrees. How heavy is the sign? So, in this kind of question, whenever you see something about heaviness, weight, mass, anything like that, always think F equals ma, right? Because that is the only formula that you actually can use that it has mass in it. So we always know we're going to have to use that. And then we know the angle each cable makes for the horizontal is 30 degrees. How heavy is the sign? So what we're firstly going to do is draw a diagram. So this is 30 degrees. 30 degrees. And then forces are both 50 newtons. So the lengths here are 50 newtons. Now, we want to figure out how heavy the sign is. So we know that we need to include F equals ma somewhere. So let's have a think about this. We want m as the unknown. We know that a, the acceleration acting on the object, on the picture frame, is going to be acceleration due to gravity, right? Because that is the only acceleration acting on the object. So we know that, which means we need to find the force, and then we will have an equation with an unknown m that we can solve for. And this is the plan that we have so far. And looking at our diagram, what we can do is find our force that is acting in the vertical plane, because of course our acceleration is acting in a vertical plane, so our force needs to be acting in a vertical plane. What we can do is add these two together and see what we end up with. So there are two ways that you could do this. You could either add the components, the I and j components of these two, or alternatively, and this is my preferred method, you can just move the vectors around and do some vector resolution. So I might actually do that just because it is, in my opinion, like, I guess it's a little bit less arduous, right? And it's a little bit more fun. So here's our diagram that I drew just before. Let's go ahead and change the and change where the vectors are. So what we're going to do, remember, whenever we're adding vectors to find our net force, we need to add them head to tail. So I'm actually going to slide this vector, that one on the right, I'm actually going to slide it down to here so that our vectors are added head to tail. And as you can see now, our net force is going to be here. And that's going to be acting in the vertical plane. Now, what we need to do is find the length of that net force. And we're going to need to do some trig. So the first thing we need to know is, we have our two sides, and we have our unknown length, which means we're going to need to use our cos rule, if you're remembering correctly from methods. So remember, we use our sine rule when we have a side angle pair, and our cos rule when we have three sides in an angle. So we have three sides. We just need to finish off this angle. So hopefully you guys remember our angle rules. If you remember this one here, right? If you have these two lines crisscrossed over, the angles between them will be the same. So this tells us this angle in here is actually 30 degrees. Because our dotted line and I'll draw it up for you, our dotted line here and this line here act as our two lines here. So this tells us that our angle is still 30 degrees, right? So all we've done is we've just kind of taken this vector, slid it down to add it head to tail, gotten this angle, and now we can do our vector resolution. Again, you could definitely do this just by finding the I and J components. I really don't find that half as much as fun. But I might quickly go through an example of how you could do that once we've gone through this. Alright, so finding our net force, we're going to use our cosine rule. So we're going to have 2 times 50 squared, take 2 times 50 squared cos 60, and this gives us that our net force is equal to 50. So you could kind of tell that this was going to be the case, of course, because we have an angle of 60 degrees in between two sides with equal length, which tells us that it's going to be an equilateral triangle, right? So it's going to be 50 newtons, and this is going to be upwards. So this is the force exerted by the string. Right. Now we're going to apply F equals ma. So the force required to hold the picture up is 50. Our acceleration is 9.8 meters per second squared. That's just a number that you're going to need to remember. If you're not familiar with it because you're not in physics or you're just not familiar with it, I'm not sure if it's in the formula book. I'd have to have a look, but if it's not, make sure you remember that. So this gives us a mass of about 5.1 kilograms. Remember, the units for whenever we're using F equals ma is kilograms. So, as you can see here, what we did is we started by drawing a diagram And then, of course, recognizing that we needed to find how heavy the sign was. We knew that we needed F equals ma. And then working on from there, we know we needed to find the net force because we had A. So we found the net force using vector resolution and then solved for M. I'll quickly show you guys how you can actually do this without using the vector resolution and just adding up the I and J components. So what you could have done is the I component would have been the sine, so you would have had 50 sine 30, and your J component would have been 50 cos 30. So we know that it's sine and cos, of course, because our I component is always sine and our J component is always sine and our I component is always, I wrote that the wrong way around, didn't I? Our I component is always cos and our J component is always sine. So it's J, this is I, and that's just from like the unit circle, right? So again, you could draw it out here. If this is our J and this is our I. So our resultant force is going to be the addition of these two J components and the subtraction of the two I components. Of course, because the I components are both being pulled away from each other, but the J components are both being pulled upwards. So our total J components is going to be 2 times 50 sine 30, and our I components will be 0. This is for our net force. So this is exactly what we got in using our vector resolution. Of course, because we only got our force acting vertically, not in a horizontal direction. Alright, so yeah, feel free to use either the components method or the vector resolution method, depending on what you're more comfortable with. Alright. Now we have a harder example. So now we're getting onto a harder example, and this is where we have an object on an inclined plane, right? So in these questions here, what we want to do is we want to rotate the axes to make things easier for ourselves, and you can see that's what we've done here. So assuming that the mass is equal to 200 kilograms, we need to find F in terms of mu so that the object can stay at rest on the ramp or move up at a constant velocity, right? So let's start with this question, right? So when the object is at rest, right, it means that the net force is equal to 0 because the applied force up the ramp is holding the object there against the friction and the force due to gravity, right? Or if it moves up at a constant velocity, we can also determine that using our F equals ma formula. So the information that we know is that the mass is equal to 200. Our angle is 30 degrees. And we know that F of friction plus F due to gravity is equal to the force, the applied force up the ramp, because our forces are balanced, leading the object to stay at rest. Right? So our force due to friction is mu times n, where mu is our friction, and n is our normal force. Right? So, what is our normal force? Remember, our normal force is this arrow perpendicular to the surface. It's the force that the inclined plane is pushing up against the object with. Alright? So, we need to figure out how we can find our normal force and our force due to gravity. So we can find our normal force using our trig ratios and our theta. So, quickly drawing this on a right angled triangle, where this is 30 degrees, of course, because these two lines are parallel. So this gives us 30 degrees here. We know that our normal force is going to be equal to mg mg cos theta. And that is our normal force. And then our force due to gravity, the component acting down the plane, is going to be mg sine theta. Of course, because like this length here is mg, so our normal force is going to be the this length here, right? And our force down the plane is going to be that one there, is equal to our applied force. All right. Now this gives us our F in terms of mu. We can sub in our theta value. So of course, theta is 30 and m is 200 and g is 9.8. So we're going to have mu times, and then we can factorize out the mg. So we're going to get 0.866 mu actually simplifying this even further, This gives us 1697 mu plus 980 equals F. Alright, and this is our force in terms of mu in order for the object to stay at rest on the ramp. For our object to move up the ramp at a constant velocity, we must have a greater force. So for it to move up the ramp, the force must be greater than the answer we covered just down here. Alright. So obviously looking at our question from right here, what we did is we essentially rotated the axes, right? We didn't consider these axes tilted. We kind of rotated them and looked at them with respect to our inclined plane instead of with respect to the ground, which gives us a lot more ability to work with the just going through the slides to work through the question. Alright, here we just have a few tips for concurrent forces. So remember to always draw a diagram and label all of the forces with directions and angles. If it's a flat surface, no orientation change needed. If it's on a ramp or an inclined plane, usually helps to set our I and J so that I is the same as the plane of the ramp. This probably isn't the only type of vector resolution question you'll get, but it covers most of the fundamental principles. Alright, now we are getting onto the second part of this modeling motion section. So here we need to consider and solve problems involving motion in a straight line with both constant and non-constant acceleration, including simple harmonic motion, and using our expressions for acceleration. So, here we have a few different expressions and equations for acceleration, and these are given to you on your formula sheet. So, if we are given a in terms of x, we need to use the equation a is equal to d half v squared on dx to get v squared in terms of x. If a given in terms of v, use either a equals v dv dx to get x as a function of v, or we can use a equals dv dt to get t as a function of v. So, this is a lot to remember. Probably use this slide as a guide when you are practicing, but otherwise try to just use your intuition more so. Alright, here we have a question here. So we have a particle being projected upwards with an initial velocity, an initial velocity of u. The air resistance on the particle is 7 mv squared. So we need to find the maximum height that the particle reaches in terms of u. And we first need to draw a diagram of what we know. So, let's start with our diagram and our force equation. So, we know that our particle, is being projected So this is going to be the force on the particle. So, negative mg, because it is going downwards. So the air resistance is pulling it downwards, and then the gravity is pulling it downwards. And from here, we can find the acceleration experienced by the particle. So, our G is of course going to be 9.8, and our F net is going to be MA. So let's find A. Of course, our M's are going to cancel out. And 9.8 minus 7v squared. And we are not going to be left with anything there. Alright. Now, since we want the height reached, we need to find x, right? Because that tells us the position. So, we have A, and this A that we have is a function of V. So, since we have A as a function of V, what we want to do is we want to use one of our acceleration equations with A and V in it, and x, so that we can solve and find x, right? So, out of the equations, what I'd like you guys to do is have a look at the equations given on your QCEE formula sheet for the for your acceleration equations. And the one that you might notice that is best is v dv dx equal to a, because this one includes a as a function of v and also x. Now we can pop in the formula just we came up with, which was negative 9.8 plus 7v squared. And now we can use this to find x. So we're going to take this v over to the side. So we're going to have dv dx equals negative 9.8 plus 7v squared over v. Now, to get x, we need to integrate, right? But we have v, we have dv dx. When this isn't what we want to isolate x. We don't want to integrate with respect to x. So we're going to use our good old trick of inverting, right? So if we invert these two, we're going to get dx on dv. We're just swapping around both these fractions, equals negative v over 9.8 plus 9v squared. Right? Now what we can do is we can integrate this with respect to v. So we're going to get that x is equal to the integral of v 9.8 plus 7 v squared dv. Alright, so integrating this, all you would need to do is use some simple linear substitution, and we would get an answer of negative 1 on 14 ln 9.8 9v squared plus c. to 0. But of course, because our velocity is all in the y direction, because our particle is projected upwards, that just means our velocity is equal to 0. And we also know that at x equals 0, our initial velocity was u. So we can use that as well to find our c value. So, we know that, I'll just rub out, I've got too far. So, we know that when we have u equals v, right? Because that is our initial velocity. When x right? So we know that our initial velocity is u, right? So we can put this into our formula now. So we know from there that our c value is going to be 1 over 14 ln 9.8 plus 7u squared. Right? So subbing this in to our original formula, this gives us that x is equal to negative 1 over 14. This is just the formula that we got before. Then plus our new c value. Now we can just combine these two ln's together using our simple log laws and take that 1 over 14 out the front. And this leaves us with 1 over 14 ln of 9.8 plus 7u squared over 9.8 plus 7v squared. Right. Now that we have done that, all we need to do is recognize, as I was saying before, that our maximum height occurs at v equals 0. So we can just get rid of this last part here, because that would be when v equals 0. And this gives us our maximum height in terms of u. Alright, now we are getting onto our modeling motion, simple harmonic motion section. So, we're going to go over the concept of simple harmonic motion and solve a few examples. So, simple harmonic motion is the motion of an object back and forth about a central point, such as a pendulum or a spring moving back and forth. So an object is said to be moving in simple harmonic motion if A is equal to the negative of the angular velocity squared multiplied by x. Therefore, the acceleration is always proportional to the displacement, but opposite in direction. As a result, the further away the object is from the center, the greater the tendency is for the object to return to the center. So the object wants to get back to the center. If you think about a pendulum, the tendency is for the object to go towards the center. So, there are a few different things you need to understand about simple harmonic motion, but typically they don't get too hard. The most difficult thing is just kind of understanding the formulas and how to use them, but once you kind of do a little bit of practice, they aren't too So the solutions are solved in the formula sheet, so you shouldn't need to derive it every time. I did say here that I'm going to do it, but I'm not going to do it today just because I want to make sure that we get to the rest of our topics. But finishing off, these are the equations that we are left with. So we have the velocity squared equals the angular velocity squared multiplied by amplitude squared, take x squared. And then of course we have our two options for the actual function describing the position of the particle with respect to time, and those are our sine and cos functions. So the other formulas that you might need to know is that the angular velocity is equal to um, to 2 pi divided by the period, and that the alpha is a phase shift, and that your frequency is 1 over the period, because our frequency is how many cycles there are per second, whereas our period is how long a cycle takes to happen. So, as you can see, at the endpoints, at x equals a or x equals negative a, our velocity equals 0. So this makes sense, right? Because when your object is moving back and forth, right, when it gets to the end, say with the pendulum, it gets to the end, it's the highest point, and then it turns around and goes back in the other direction. So its velocity equals 0 right at that end point because it's no longer going one direction, it's turning around. And what you also might see is that when it's getting up to the top, to the end point, it's slowing down. So that's another indication. So acceleration is always in the opposite direction to displacement. At the center of motion, the acceleration is equal to 0. Right? And then the maximum speed, and hence maximum and minimum velocity, occur at the center of motion. So when the object is in the middle, it's going the fastest. Whether it's the maximum or minimum velocity depends on what direction it's moving in. Just like whether it's a positive or negative, but the speed, like the absolute value, will be the maximum. And then the magnitude of the acceleration is maximized at the end points. So this is because when it gets to the end, it is turning around, so its velocity is changing a lot at that point because it's turning around, which means that the acceleration is higher because our acceleration is the rate of change of the velocity. So this slide here that we have is particularly important to remember, right? Because these are all of the values that questions are going to ask you. They're going to say, find such and such value at the maximum speed, so forth, for all of these different values. So make sure that you jot these down. If at the center of the motion the object is not x equals 0, then we can use these following equations. Don't worry too much about these ones. You can use them, but you really don't see them a lot, if at all, in any of your textbook questions. Just some quick tips for simple harmonic motion. If you need to use the sine cos, try to make the initial phase shift to 0 if you can. So choose sine or cos. Choose whichever one is easiest. Actually think about it. Don't just kind of choose whether it's sine or cos arbitrarily. Think about it. Think about the shape sine curve, the object is starting at the equilibrium. If it's a cos curve, it's starting at an end point, right? Because our sine curve starts at the origin, but our cos curve starts like up above with a positive line intercept, typically. If the particle starts at the positive external motion, what I was saying, use x equals a cos wt, and then the negative if it's an extreme negative. If the particle starts in the middle of its motion with a positive velocity, use sine and put a negative at the front if it's a negative velocity initially. If it starts anywhere else, then you will need to use the phase shift alpha, either sine or cos, that's okay. To find the phase shift, substitute the boundary conditions to find A and alpha. So you'll be given values that you'll be able to substitute into your equation for x to solve for the unknowns A and alpha. Alright, let's go through an example. So, here we have a particle oscillating with A equals negative 16x. Its speed at the origin is 24 centimeters per second. Find the velocity squared, what are the amplitude and period, and find the speed and acceleration when x equals 2. Alright, again, pause the recording, have a go at this, and then check the solutions. So, the first thing that we are going to do is write down the information that we know. Right? So we know that its speed at the origin is 24 centimeters per second. We're going to convert this into meters per second. So we have 24 centimeters is going to be 0.24 meters per second. So we can just leave that as is. Then we need to find the velocity squared. Right? So let's remember our formula or our equation for acceleration, where we can incorporate both v and x. Right? And we're going to use this one because we want to find v squared, and we know that its speed at the origin when x equals 0 is 0.24. So, to find v squared, we can use our formula. Remember, we have v squared equals the angular velocity squared outside of a squared take x squared. So, we know that our acceleration is equal to the negative angular velocity squared x. Right? So, from here, we know that our, because this is equal to negative 16x, our angular velocity is equal to 4. So we can substitute this in over here, so we can have v squared equals 4 squared. Now, how are we going to find A? Our amplitude. To pop into this formula. So we know in to find our amplitude. Amplitude squared, take 0. Our velocity squared is 0.24 squared. We can find A from here. So this gives us an amplitude of 0.06 meters. Now we can find V squared. So we're going to have V squared equals 16. And then we're going to have 0.036. No, sorry, 0.36. 0.36. Take x squared. This gives us V squared. Now we've already found amplitude. Now we want to find the period. So remember our period is given by, so we're going to have 2 pi over 4, which gives us pi on 2 seconds. Now we want to find the speed and acceleration when x equals 2. So, a at x equals 2 is going to be negative 16 times 2, which is negative 32. Presumably that's in centimeters. And then we also need to find the speed. So our speed is going to be v squared equals 16, 0.06 squared, take 2 squared. We can find our velocity, and from there we can find our speed. I just realized we would need to convert, we can actually convert this back into centimeters, even though technically the standard unit is meters, all the other units are given to us in centimeters, so we can't mix them, but that is okay. So this gives us that our velocity is equal to 22.62 centimeters per second. Just be careful with the units there. Alright, that is it for that question. Just as a summary of modelling motion, remember our net force is the sum of all of the forces acting on an object. Make sure you always draw out a force diagram. Resolve into horizontal and vertical components. Rotating the axes if you need, such as if there's an object on a ramp. And then using our formulas given on the formula sheet. Remember to kind of really think about what equation you're using, what formula you're using, and what variables and numbers you want in there. Don't just kind of pick one willy-nilly. And think, if you're trying to solve for a particular value, you always want that value in there, and then for other information that you know or you already have an expression for, you can also have those values in there too. So, for simple harmonic motion, remember the formulas, they're on your formula sheet, but make sure you remember that slide about what values are maximized and minimized at certain points in the the motion of the object, right? So when the velocity is the greatest, when the velocity is the smallest, acceleration displacement, so forth, because those are primarily what questions will ask you on. Alright, now let's get on to sample means. So, the syllabus requires you to fulfill these 3 dot points. What we're going to focus on to begin with is examining the concept of the sample mean as a random variable whose value varies between samples, where x is a random variable with mean mu and standard deviation sigma. So, let's have a look here. A sample is a small part of a whole, or in other words, a subset of the entire population. For an example, taking the height of 100 people in a population would be a sample. From the sample, we can draw inferences about the population. So, we can have samples from x1 to x2 to xn, where n is the sample size. So, our samples are independent of one another, so one sample is not going to have an effect on another sample, and the samples are identically distributed. So if there's an underlying distribution behind each sample, such as a normal distribution or a binomial distribution, such as the things we've done in methods, these distributions are the same. So, from methods, let's consider the binomial distribution. If we were measuring the number of 6s rolled in 20 rolls, 20 trials, p equals 1 on 6. This is the kind of question we would look at in methods. However, what if we wanted to do this 500 times? We could have a binomial distribution with 10,000 trials, right? Because we have our 20 rolls multiplied by 500. Alternatively, we can treat each set of 20 rolls as an individual experiment, and thus we can run the experiment 500 times. So, essentially in Specialist, what we're doing differently is instead of focusing on individual trials, we're actually taking those trials and counting them as sample groups, right? So, by the second assumption, each of these samples follow a binomial distribution with n equals 20, p equals 1 on 6. Remember, because the distribution of one sample is always the distribution of the other samples. And the sample mean is simply the average of the values of each sample. Similarly, it can also be thought of as the average of all of the random variables. So we can find the sample mean x by adding all of the values of the samples divided by the number of samples that we took. Alright. So, there are some other important things to note about x, is that x is the mean, and our standard deviation is still sigma. But we'll see what happens to these variables when we look at the distribution of the sample means. So, we have a quick simulation here, where we suppose that a population consists entirely of 0 and 1. Half the population is 0, half is 1, thus the population mean is 0.5, obviously. What will happen if we take samples of increasing size from this population? The results are as follows. So as you can see, as we take more and more trials, we go from n equals 1 to n equals 20, right? We have more of a spread distribution, and the probability increases until the sample mean reaches 0.5, and then decreases again. So as you can see, when we have a small sample size, our distribution is very up and down, but as we increase the sample size, it's getting more and more evened out, and it's approaching a normal distribution, sorry, a binomial distribution. So, as n increases, the probabilities on the lower and upper ends shrink, and the probabilities in the middle are relatively larger. And then if the if the number of trials were to increase even more, our distribution would become even smoother, even more bell-shaped, even more like a normal distribution. All right, let's get on to our central limit theorem. So, in general, as n increases, the distribution should resemble the normal distribution, or a bell curve. And this is true no matter what the population distribution initially looks like. So as n becomes larger, we have a better approximation. So the properties of the sample mean are that the mean, mu, is the same as the population mean, but our standard deviation is the population mean divided by the square root of the number of trials that we took. So as you can see, even though the mean of the population and of our number of samples is the same, however the standard deviation differs. The central limit theorem is actually something that's important to remember. I remember there was a question about it on my external, so I'm lucky I remembered it, so make sure you do jot it down. As we can see here, when n is equal to 30, our distribution always approximates a normal curve. And as the, or even if the population distribution is not that similar to a normal curve, as we conduct more samples, our measured data approaches a normal curve. And this occurs when the number of samples is greater than, or is equal to or greater than 30. So, this is just another way that we can write the central limit theorem. In reality, though, we never know what the standard deviation of the population is, so instead we just use a sample standard deviation, S. And this is generally for larger sample sizes. So, let's go over the differences between x and x hat. So x is a single element chosen at random from the population. The distribution of x is the distribution of the whole population, and it has parameters of mean, mu, and standard deviation, sigma. This is more so what we were looking at in methods, right? X hat is the mean of the measurements of sample size n taken from the original population. And the distribution of x hat is the sampling distribution. So it has parameters of mean, mu, and standard deviation, sigma, on root n, also commonly referred to as the standard error of the mean. So standard error, is represented by capital E. And we'll get into a little bit more of standard error when we get into confidence intervals. So, let's go through a quick worked example. So here we have a population with a mean of 50 and a standard deviation of 6. So a mean of 50 and a standard deviation of 6. What are the mean and standard deviation of the sampling distribution for n equals 16? So the mean is 50, because remember it's the same. However, the standard deviation is going to be equal to sigma over root n, which is 6 on root 16, 6 on 4, which gives us 1.5. For part B, we have the same thing for our mean, and then our standard deviation is equal to 6 over root 20. I'm not sure if we can simplify that down. I don't think so. No. Which gives us about 1.34 approximately. Alright. So, a quick summary of sample means. Remember, x is a random variable with mean mu and standard deviation sigma. The sample mean x hat is a random variable whose value varies between samples. And the sampling distribution is a representation of all possible sample means and how likely each value is. The parameters of the sampling distribution, mean equals mu and standard deviation equals sigma on root n. As n gets larger, the sampling distribution resembles a normal distribution, even if that's not what the population looks like. And as an approximate standard normality for large sample sizes, when n is greater than 30, we can approximate it using x hat take mu on s on root n. Alrighty. Now we are getting into confidence intervals. So we're going to be going over interval estimates, confidence intervals, and then the interpretation of confidence intervals. So, an interval estimate is a range of values for a statistic, such as between 25 and 100. A point estimate is an exact value, so something equals something. So, if we wanted to estimate the amount of Year 12 students that own a laptop, we take a sample of 100 students and find that 60 of them own a laptop. Therefore, the point estimate that the mean of the population is equal to 60 tends to be unreliable because it's so specific, and you really can't expect a single sample to accurately represent the whole population. To be safe, we use an interval estimate instead. So we say that mu lies between 55 and 65. Right? So, a confidence interval is an interval estimate with a certain confidence level attached to it, which just means how certain we are that the attained result is repeatable. So in the previous experiment, we might say that we are 95% confident that between 55 and 65% of Year 12 students own a laptop. So the lower bound is the lower confidence limit, and the higher bound is the higher confidence limit. As you might be able to guess, as the confidence interval or the confidence level increases, the interval increases too. So to be more confident about a result, we have to make it more vague, right? You could be 100% confident that between 0 and 100% of Year 12 students own a laptop, right? But that wouldn't tell us much at all. So when we are attaching confidence intervals, if you say have a 90% confidence interval, then your interval of values might be smaller. So then we might have between 57 and 62. Alright, our confidence interval formula is written on your formula sheet, so don't worry about remembering it. But remember, we don't know the sigma or the standard deviation of the population in practice, so therefore we use S instead, where Z is the quantile of the normal distribution that we are considering. So, getting back to quantiles, if you're using your graphics calculator, you can just compute the relevant z value off of the standard normal curve required to construct a confidence interval. But otherwise, these are the ones I'd consider memorizing. Even even so, like you yeah, you would most likely need to remember these ones, and definitely the 97.5th quantile, which is 1.96. That is the most common one. Alright, so how can we determine what quantile we need? It depends on the percentage of confidence interval that we want. So, if we want a 1 minus x% confidence interval, the z value that we require is at the 1 minus x on 2% quantile, right? Because we have it on both ends, as you can see here, so that's why we're taking 1 minus x on 2, because we're splitting that extra area by 2. And then, of course, these are our z values for quantiles and specific confidence intervals. Again, this one here, 97.5th, 1.96, 95% is the most common. As you can see here, this is an illustration of a 95% confidence interval. So we have our mean in the center. Then we have our 95% area, or 0.95 area. And then this is within 1.96 standard deviations on either side of the mean. What you can see here is that we have a 2.5% range on either side. This isn't super accurately represented, of course. It's just drawn like this so you can actually see the endpoints. But we have a 2.5% area on either end because, of course, we have a 95% confidence interval, so the leftover is 2.5% on either end. All right, we have a worked example here. So here we have a group of 100 soccer players practicing their free kicks. Each player takes 10 kicks each, and it is found that the average number of goals scored per player is 3.6. The number of goals scored is known to follow a normal distribution with standard deviation 0.6. Let's do our first one. Find a 90% confidence interval. So let's have a look back at our formula. So we're going to have our mean minus our z score value multiplied by the standard deviation divided by root n. So we're going to have 3.6 minus our z score. We want a 90% confidence interval, which is a z score of 1.645. Multiplied by our standard deviation over root 10. Then we're going to have the same thing but plus over here. And I'll figure out what this gives us. So this gives us an answer of between 3.0 29 and 3.912. And this is our confidence interval. I'm not going to go ahead and figure out the rest of those just because they are exactly the same procedure, but please go back and figure those out on your own just for revision purposes. So let's get on to properties of confidence intervals. So we can calculate the width of the interval by subtracting the endpoints from each other, giving the width of 2 multiplied by the z-score s on root n. Another term worth recognizing is the margin of error, z multiplied by s on root n. So if n increases and z and s are unchanged, then the width decreases. Or in other words, the confidence interval is narrower with a larger sample size. And this makes sense, right? Because if you have a larger sample size, you can kind of be more sure that the sample that you're taking is more indicative of the actual population, right? Because you're taking samples from more people, you're less likely to get kind of outliers, skewing things, you're just taking a greater proportion of the population. Then if we have a larger quantile, we have a larger z value and a wider interval again. And note that x not included in the formula, the mean not included in the formula, changes the mean only translate to interval. It doesn't affect the size. And then if the standard deviation increases, then the width increases, of course, because we're increasing the measure of spread. All right. Simulating confidence intervals. If you would like to have a look at that simulation on that website, please feel free. But otherwise, we are going to move on. So when we're interpreting confidence intervals, from the simulations, you should find that some or most of the confidence intervals contain the true mean, whilst some won't. In the long run, however, if you consider 95% of confidence intervals, 95% of those intervals will contain the true population mean. So if you calculate n 95% confidence intervals, find how many of them contain the true mean, then calculate 0.95 times n, and those numbers should hopefully be similar, right? So now what I'm going to do is get onto some external exam advice and some prep. So my advice for external exams is to make sure that you go through every single dot point on the syllabus and write the general process for that type of question and any strategies that you pick up. So what I did is I copy pasted the whole syllabus and wrote notes under each of the syllabus dot points just to make sure that I didn't miss anything. And then once you get the basics, make sure that you practice like really hard questions, right? Don't kind of just practice the easier questions. Make sure you really challenge yourself because that's the time that you learn the most effectively, the most efficiently, and you're really extending yourself. So this develops your problem-solving skills for complex and familiar questions and actually helps you understand the concepts way more thoroughly. It's also just more entertaining, in my opinion. If I'm kind of stuck doing easy questions, I get kind of bored. And then make sure you use as many resources as you have available to you. So that might include different textbooks, study guides, libraries, or even Googling questions. really look in as many places as you possibly can. It's not listed here, but you can even go and look at the other states' external exams. Like if you look at WA or Victoria, New South Wales, all that kind of stuff, some of the content really won't be relevant to our content, but if you're really looking for some more things to do, you can have a look through and see if there's anything that looks relevant to what we've been doing, and have a go at those questions too. The good thing about that is also they usually make the work solutions available online. So you can check your answers, and if you're confused about getting an answer wrong, you can usually figure out where you went wrong. This is just a quick snip of the beginning of my external exam notes, just because, kind of an example of what I'm talking about. So in the green, I have the syllabus dot points, and then underneath each, I either have, if there's any formulas that I need to remember. So for example, when we're looking at vectors, all these formulas about x, y, and z, and unit vectors and so forth are not on a formula sheet, so I put those there. The equation of a sphere, the midpoint of a vector, equation of a straight line, are not on the formula sheet, so I wrote those down. Then I also wrote down any strategies. So for proof by induction, I have using index laws, factorizing, expanding the right-hand side, trig identities, making the denominator the same, and using factorials. So those would have just been things that I came across when I was doing more difficult questions, and I came across strategies that I popped in there to just make sure that I was constantly reminded of them. Even if I did those questions like earlier in the year, nowhere even near the externals. Then this is just a special document that I made specifically for integration. So this is another thing that you could do if you're having trouble with a particular topic. So I kind of made a table, as you can see here, of a particular type of hard question that I had come across, and then things you could potentially try to solve that question. So if we have something like a denominator being a quadratic with a constant for a numerator, you could factorize and use partial fractions. You could use inverse tan. If you can't factorize, you can complete the square, and it might be an inverse tan integral. And then you can use linear substitution for the linear function inside the brackets. So as I said, that really is just making sure that you're taking thorough notes and doing complex questions so that your notes really are useful to you. Getting on to internal exam prep. If your teacher gives you a list of revision questions, practice them until you would rather die than do them again, right? This really cements the process in your brain. Another good thing to do if you're really dedicated is kind of brainstorm the ways in which these questions could be changed to be harder. So typically that's what teachers will do. If they're going to give you a complex unfamiliar question, say on modeling motion, right? They'll give you like an easier question and then change a few aspects to make it complex familiar, complex unfamiliar. So if you brainstorm some ways to kind of make that question harder and then figure out how to do it, so it might be something about going backwards, using only variables instead of numbers, proving a particular expression or equation, or merging two different topics together. An example of this that I have here is in our revision, we got something about a cylindrical hole being drilled through a sphere, and we found the volume of the bead using a volume of solid revolution. And it came up with a few different ways to make that question a little bit harder. So, general exam prep, every single time you make a mistake, make sure that you make a note of it so that you remember not to make that same mistake on the day, especially if it's something that you find yourself doing a lot. A lot of students have an amazing understanding of the concepts, but are like just deficient in algebra skills, which is really important, especially in the tech-free exams. So make sure that you're practicing your algebra skills. You're not taking any shortcuts. If it's a tech-free question, make sure you're forcing yourself to not use your calculator. And kind of also learning new methods to use in algebra, because you kind of do like learn new cool things to do when you're doing a lot of questions. Another thing you can do if you're really struggling to kind of keep up your motivation is kind of read some books about it. Some of the tips that I got from books were, firstly, if you feel yourself losing focus when you're studying, make sure you oxygenate your brain. That seems pretty common knowledge, but a lot of people don't do it. Doing questions that are kind of just too hard for you is the most productive way to learn, because that's when you have to put the most effort into what you're learning instead of just kind of like breezing through and following a particular procedure. You're really putting a lot of effort in your brain into learning. Obviously, this doesn't work if the question is way too hard for you and you have no idea what you're doing. But when it's just too hard, that's really when you learn the most efficiently. Of course, then because you're putting more effort into when you're learning, you can spend less time studying too. Another good thing, which sounds a little bit psychotic, is to listen to the same songs over and over again. I still do this in university. If you kind of get like a pretty regular, like an upbeat song, kind of like a pop song, and listen to it on repeat, it kind of puts you into this zone. Essentially, it's actually shown in studies, which is crazy. But it puts you into this zone, and it's really easy to focus when you do that. For high achievers, the most common source of lost marks isn't lack of knowledge, but it's A, making lots of small mistakes, and B, getting stressed on the day. So for avoiding making small mistakes, make sure that you understand the content, right? What I have down here is mostly about checking your work, which is, I guess, just a patience thing, which you need to get better at. But really do make sure that you understand the content too, because when you really understand the content, you're far less likely to make a conceptual error. And then getting up to like kind of like the small, really annoying errors, make sure you've written down every formula correctly. Infamous example, when I was in year 12, I didn't check the formula for the area of a triangle in my formula sheet, so I forgot the half out the front. And that was the lost mark that pushed me over the edge from getting a 15 to a 14. So I ended up getting like 92 point something. And if I just put the half out the front, I would have scraped through to a 15. Anyway. Make sure you copy down your values correctly, that you haven't misread a number, especially if your writing is a little bit messy. In tech-free tests, mentally check your arithmetic. This is really important. It's really easy to kind of do silly things, like 2 plus 3 is 6 kind of thing. Just really make sure you're checking over everything. Be really kind of harsh with yourself and go through and check everything that you've done. It's really good if you have a really good understanding of the content, so you're able to do the questions fast and then go through and check all of your answers. And then also as well, figure out what mistakes you make the most often when you're practicing and focus on not making those on the exam. If you tend to find that you get stressed, figure out some strategies that help. Something that helps is practicing questions until you're so bored that you'd rather die than do it again. You're burning the process into your brain. So even if you get stressed and feel like you are forgetting the process, it's so burned into your brain that you will not forget it. And then probably the most important thing is to just don't talk negatively about it to yourself. Um, if you're constantly thinking, I'm so stressed, I'm going to make so many mistakes, yada, 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 it puts yourself in that mindset, right? Whenever I went into a maths exam, I had a massive, I was, I was massively confident, right? Like to the point where it was kind of annoying, probably, you know? You're almost delusional. You need to think so positively about it, that you just kind of that you're able to do better because your brain is like more open to thinking of ways to figure out answers, more open to not making mistakes, that kind of thing, right? During an exam, make sure for complex questions your communication is on point, write all your formulas, define all your variables, write headings, draw separate diagrams, um, and have a look at the marking sheets if those help you as well. And always remember to, or that if you have a 1 mark question, they generally only require an answer with units if it's necessary. Again, make sure you are looking after yourself, physically and mentally. There's a lot of pressure, but there's a lot of pressure to do well from a lot of different people. But really just remember to, take it as you go. It's going to be okay. At this point, you have 4 months until your externals. And I mean, you might have an internal exam coming up, but that's only worth 15%. So really just try to relax. Anything is possible. If you get really stressed about it and really worried, that's when you're going to kind of miss out on life a little bit, right? You want to make sure that you're enjoying your life, and doing well as well. So that means both not studying every second of the day and also not procrastinating study and feeling guilty every second of the day for not doing it, even though you didn't even end up getting anything done, right? Make sure you're not doing either of those. Make sure you're studying a little bit and then not feeling guilty when you are not studying and enjoying your life. All right. With all of that being said, we have a few questions at the end here that we don't have time to get to today. But please feel free to go through the slides and have a go at these. And the answers are available at the end of the slides as well. With all of that being said, that is it for our content today. I wish you guys all of the luck with your external exam. I hope it goes really, really well for you. I hope you have a fantastic rest of your Year 12 experience. And have a great rest of your day. Alright, see ya.